Got a few people on the stream now. I'm calling that live for a minute. I gotta get my lights on. They look terrible. Just might chill out a bit and see if anyone else shows up before starting. Hey Sam. I've got at least 2 chat windows open, so if things don't work out, that may be the reason. Yeah, Luca, we can certainly see the recording on Echo later. I'm just going to record it on my computer and then upload it to Echo. So it'll be on Microsoft Streams first. That does a recording automatically. So that'll record everything and it'll be available in about 20 minutes after the lecture. And then on Echo 360, I have to edit the video and then upload it. So maybe we won't get started for a few minutes. It's only 9:04. We can let people roll in and see if a few more show up before we start the lecture. But if you've got any questions, then jump in right now and we'll see if we can find some answers for you. Hey Chris, you? It's only a little bit crazy to have to do lectures at 9 o'clock in the morning when we don't have a room booking, isn't it? I at least have to be standing up. You could be in bed or eating breakfast or just relaxing, which is cool. I do have my coffee. Melodic Maple is Oscar. Well, welcome to you, Oscar. I'm glad that you've got such a whimsical Twitch username. Well, whoops. Okay, so we've got about 40 people watching. There's 30 of you watching on Microsoft Stream through Microsoft Teams, which is really cool. I've also got about 10 or 15 people watching on Twitch, which is exciting, and there may be some people watching on YouTube as well. If you want to chat with me, then I think that the Twitch stream is the one with the lowest latency. So on Microsoft Stream, there's about 45 seconds delay between me speaking and you hearing it. and on Twitch it's about 10 or 12 seconds. So if you have a question or you want to discuss something with me in real time, Twitch is the place to go. I don't mind where you chat with me. I've got two windows open with Teams open and an interface to the chat from both YouTube and Twitch together. So if you ask me a question in either of the chats, I'll get to it, I think. I'm not quite sure how my voice is. It sounds a little bit boomy in here. I guess I'm going to keep working on my setup. You know, last time we had a stream lecture, I was in my office, and then it became clear, like over that weekend, that we were all going to get kicked out of our offices. So I took all my stuff home from the university, got set up in my house. I've got all kinds of computers and equipment in big piles because we're pretty much locked out of the building until the end of June. So everyone was in this huge panic to just like pick up all of the equipment they need for their teaching and research and get it home so that we can continue doing our job, because we really want to keep teaching you guys and keep researching. Let's make sure I can see the chat properly. Sometimes I get a bit confused in Microsoft Teams about, no, I want the stream chat. This is the stream chat, right? I'm always confused about which chat goes to which thing because everything you do makes a new chat in streams. Oh, thanks, Mitch. Sounds good to him. So let's start with some work for the morning. Our topic for this week is going to be functions. Finally, we're getting into functions. We've done so much work with very basic, small, detailed computing structures, and we finally get to something which is a little bit more abstract, a little bit more high level, and you feel like you could get some real work done with it. So I probably don't have my my sound set up here, but I'll just make sure we get that. I wonder if that's coming through or not. Well, they're singing hallelujah, so that's what we should be saying right now, because finally we have a high-level structure that we can do our programming with. This is where things start to get really exciting in this course. We've gone from digital logic circuits, we've started to look at individual operations which would take just one cycle on a CPU to do. We've worked out how to move around in a program and how to make decisions about which line or which machine instruction we should execute next. And now we get to have our functions, which are a higher level operation or a combination of multiple instructions in a row that will get executed from our perspective as if it's just one thing. So we're taking a bunch of instructions and squishing them into one little command. I might just I don't want to have multiple obses. And I should also start recording, actually. Now, it's easy to forget all these things when I'm just getting started on a new system, but I might do left-hand side. Okay. So today's lecture, functions, we're going to be talking about basically what the point of functions are at all, a little bit of a higher level introduction into what these things might be and how we use them in assembly. I think today we'll also get to this idea of calling conventions, or perhaps the rules or written rules. They're not unwritten rules because they're written down. The written rules of how to interact with functions when you're doing your assembly programming, that you've agreed with other programmers to all do the same thing so that you don't mess up everybody else's programs. And then in the second lecture this week, we'll predominantly talk about the stack, which is a part of memory that we use for storing information during our program, our functions. Yeah. So those are the 3 topics for the week. But the functions point is the main one today. This is the main thing we're going to be talking about. Why functions at all? So the big picture idea here is that the reason we use functions is because copy pasting sucks, right? So far, if you've wanted to do some procedure in your assembly program and then you wanted to do it again, you would have just had to select those lines of code in Codium, copy it and paste it later and do it again there. You of course can branch back to different things, but some people have found that there's already limits in how your branching might work. Particularly if you branch to somewhere and then you want to branch back to where you were before. And if you're just using the basic B instruction, the basic branch instruction, then it's not as easy to really navigate to something and then come back again, which is what we really want to do when we're doing something like a function. So the whole idea of copy pasting code around your program, that's like should be anathema to us as programmers. We want to have it so that we write our procedure once, and if we need to use it multiple times, then that bit of code gets used multiple times. We don't need to write it multiple times in our program. So this is just the big picture idea of why we want to do this. Let's have a look at some functions. I'm sure you're familiar with functions. It's something that everyone has done when they're starting to write code in first year programming. You know, here's a typical little Python function here. This is the argument x, and then this is what we're doing to x. We're adding 1 to it, and then the return command here means that this part of the code, this answer is getting returned to the bit of code which is called the function. Functions usually have a name, right? And then we've got some kind of indication that what we've got is a function. Here's the same thing in a couple of different languages. We've got a version in Java. So here's our return value, the same thing, return x plus 1. Here's our argument, x, our input. This is the input, this is the output, this is the work, x plus 1. Here's the name of our function, plus 1. And then we've got this other thing, which actually doesn't make sense. That should probably be int, right? Because that's the name of the type of the thing that our function is returning. Public string plus 1 int x. That's not right because x plus 1 is not a string. Here's a function in Haskell as well. Slightly different way of writing them. Of course, when you're writing functions in pure functional languages, you often don't have a name for them. So this function is nameless. Oh no, it does have a name here, plus 1, and then here's the body of the function. We could of course have a nameless function as well, just a lambda expression. Here's our input, and then the output of the function is just like whatever comes out at the end of that expression, the last expression which is evaluated. String bruh, yeah, indeed. Very much string bruh. I'll just make sure that my, I want to make sure that my obs is right. Apparently my head's always in the way of the slide. Maybe if I do it on the right hand, no, that's the wrong one. This right hand side. I think that's the smallest head you can get. I've got to have my head somewhere, otherwise what's the point of me being here? So I'll put it to the far right. Face cam is covering the slide. I need more, one of you guys to sit here and fix my obs for me in real time. Okay, and I probably also need another monitor with a preview on it so I don't make that mistake. Okay. Whoops, I've gone way too far forward. So before we get into the details of how we do it, let's just ask ourselves what a function is. And I've got a few analogies to talk to you about that are kind of ways of describing functions. So this is the first analogy. functions are kind of like a pipe. So a pipe has one end where you put things in and another end where things come out. And maybe this is the end where we're putting stuff in, and over here we're getting things out. And then in the middle, there's some work getting done, and we don't quite know what that work is. I guess it's some kind of black box. There's some processing going on, or maybe nothing is happening in that pipe. Why is this a good analogy? Well, I guess pipes can kind of plug into each other. The output of one pipe could go into the input of another pipe. That's something we can definitely do with functions. But I suppose it's in the context of this lecture, or discussing this in assembly programming, it's not the best analogy. So a better analogy, and this is the one that I call the core analogy of this course for functions, is that functions are like there and back again. So I think maybe some of you know what there and back again is, or you recognize that reference, right? That's from The Hobbit. So The Hobbit is this story where, there's, Bilbo Baggins, a quite unassuming creature, lives in a little village, and then one day he meets the wizard called Gandalf, and Gandalf says, okay, all these dwarves are going to come and take you on an adventure. And they go on an adventure all the way up to some mountain range and across the mountain range, and then they meet a dragon, and there's a big battle. And then after this big adventure, all this action happens across the other side of the mountains. Battles, people die, treasure is found, friendships are made, allegiances are forged. Then after that, he comes all the way home. So this is the there, and the other one's the back again. My tablet doesn't work today for some reason. Moved all my stuff home, and then half my stuff doesn't work anymore. So that's where we're at with this class. Yeah, so this is the analogy that I want you to think of when we're thinking about functions. Because when you're dealing with assembly programming, and you've got a list, when you think of your program in assembly, what it is a bunch of memory with machine instructions in it, right? You've got your machine instructions, and your CPU is sort of ticking along on each instruction, reading it, decoding it, executing it, going to the next one, reading, decoding, executing, going to the next one, etc., etc. And really, a function in your disco board is a place. It's not a thing. It's a place in your memory where there's some instructions that you want to be using multiple times for different kinds of things. So this bit could be called your function. So if your code gets to here and it wants to run your function, then you need your program counter to go on a journey over to this place in memory, pick up that instruction, work on these instructions that you've set up here, and then when it gets to the end, it's done its work, it's had its battles, it's found the ring, had adventures, it comes all the way back. So really, your function is going somewhere else in your program, which is a place in memory, and then coming back again to where it started. So this is the COMP2300 analogy for functions. Keep it in mind when we're going through the rest of this lecture. It comes back again. I guess, for those of us who are maths fans, I guess I'm among them. When I think of a function, I think of something more like this, right? The typical kind of mathematical expression of a function, which really has some useful features. We've got some inputs, A and B. Our output isn't really strictly defined, but it's everything on the other side of the equals sign. That's the output of the function. A good thing about functions in the mathematical sense is that they're composable. You can take one function and call it from within a second function. So when we're thinking of the pipe analogy, like if you go inside a pipe, it's hard to imagine that inside the pipe there are lots of other pipes, or that you could, for instance, use this pipe down here from inside that first pipe. So in this analogy, in the mathematical way of representing functions, your subfunctions can be used just by putting their name there. And I guess this works for the there and back again analogy as well, because within your journey, you could be having some sub-journeys. I've lost my my pen here. This could be a journey over here where, because they're in the caves and meet the Goblin King or whatever they do. And then over here they go and meet the wood elves in the forest. So there's potential to have like little sub-adventures or sub-journeys within that. But this analogy works as well, the typical mathematical analogy. So now we get to just describing what these things are in assembly. So here is your memory. These are your machine instructions all lined up. You know, each of them has got an address in hex. And then when your function gets called, this is going to be a function call, you're going to a different place in memory where you've got some other machine instructions all lined up. And then this is the program counter, PC. Whoops. PC is going to let you go. Whoops, go down there. Whoops, my pen really doesn't want to work. Program counter increments here. When you do the function call, your PC changes, you go to this part of your code, execute that, and you come right back where you started. There and back again. So this is a function call, which is what we call the action of the function getting executed and going all the way back. So I guess if I were to say, when does a function call end? It's after this has returned. And when does it begin? It's just when you instruct your disco board to move to this other part of code and execute that. So talk time. I guess it's a little bit more difficult to talk when we're delayed by a few seconds, but talk to me about why we can't do this with branch B, or why we could do this with branch, the regular B command. I'm going to keep an eye on the chat, and let's just take a second to think about this. Can we do it with B? I'll just type the question in. Question time. Can we do there and back again with just B? Someone says no. Yeah, omnipotent Oebear says no. Oh, it's an owlbear, sorry. Sorry, omnipotent owlbear. I'm terribly sorry about that. Misspoke. No, you can't. Melodic Mabel says you can, but you're going to need to move the current PC somewhere into a register. That's a good point, because we need to store where, we need to remember where we were. So when you're going in, when you move somewhere else with your function, you have to remember what this point was. Oh, I can't get anything to work anymore. You have to remember where this point was so that you can actually get back there. Yeah, I don't have all of the interesting plugins that people have to display chats on their screen. I'll try to work something like that out for next time, but I can't show you all the chats at the moment. Yeah, and Jackson says technically yes, but requires you to store the current executable point, PC, in accessible memory or a register. Absolutely, Jackson. So I guess where we get into trouble is when we try to be back to memory, because if we've stored our program counter in a register, can you use the B instruction to get back there? let's just have a look at our cheat sheet for a moment. Go into the COMP2300 websites, resources, books, links, and other good things, and let's look at the cheat sheet. Okay. How do I zoom? Someone tell me the key command to zoom in Ubuntu. Yeah, I don't think you can. Someone said, Adam Rowland said on the Twitch chat, or the YouTube chat actually, that you can't use a register value in B. And that's exactly what we see here. So B has to have a label in there. So you have to give the location that you're going to as an immediate. And when you're writing a function, you don't know where you need to go back to when you're writing the program, right? Because any part of your program could be running this function call. It could be running it at any time. So if you're at the end of your function and you wanted to go back just to here, that's fine. You could hard code it in there with B. But if your function is then getting used down here, then you don't know where that's going to be. So you can't have B's with multiple values in it. So what we really need is a different kind of command, this one called bx, which can change the program counter to the value stored in a register. Yeah, so Oscar says you can use mov to mov a register value into a PC. I think that something bad might happen if you try to do that too much, but you potentially can. Yes, so there's sort of ways to get around it. Yeah, okay, thanks for the great little discussion, everybody. It's fun to try this online and get some live feedback from everybody. Yeah, I guess the question was, can we do it with B and not can we do it with mov? So then, yeah, you can use mov as Jackson suggests. Yeah. So now we get to a list of questions about functions, which is going to be what we're pursuing for the rest of this week. So the first one and the most crucial one, how does your program know where to get back to? We know where to go because we've got the label of the function. We need to know where to come back to. The second one, how do we pass information, that is the parameters, into the function? With all the function analogies we have, there was sort of a clear place where the input was. But how do we know what the input is for a function in assembly programming? I don't know, open question, we'll talk about it. Very similar question, how do we get the information out? How do we get these return values out of the function? And then finally, can we have some scribble paper? So I guess what I mean by scribble paper is a place to do some work inside our function where we're not going to mess up all of our existing work that we've done in the other parts of our program. And this scribble paper one is perhaps one of the most important ones and the one which is easy to trip up on as a new assembly programmer. Because you know that when you're in assembly, you can do anything. You can change the value of any register. You can change the value of memory. And if some other part of your program is relying on those registers or relying on that memory, then you're going to be in a very bad situation. So what we need is some scribble paper where we can be reasonably sure that we're not going to tread on any other information stored by other parts of your program, and that it's not going to distress other programmers if our function is using these registers or memory. So that's what I mean by the scribble paper. So I guess just a note overall, it's easy for me to misspeak, but parameters, arguments are going to be different words for the same thing in this lecture. They all mean the input to a function. The arguments of a function are the inputs. The parameters of a function are the inputs. Different words for the same thing. So now I guess we're going deep down the analogy path, but another famous story which includes going there and back again is Hansel and Gretel. So perhaps you know the way Hansel and Gretel goes, but if you don't, I'll just give you the quick overview of it. There is a woodcutter in the forest and his wife, and they have two children called Hansel and Gretel. And they're very poor and there's a famine, and they decide that they can't keep their children anymore, so they're going to abandon them in the woods, which is very cruel, but I guess this is one of these old fairy tales which are cruel. So Hansel and Gretel overhear this plan, and they come up with an idea of how they can outwit their parents. So Gretel gathers up some little rocks, and when they're being led out into the forest, she's dropping the rocks one by one on the path. And then when they get abandoned in the forest, then she can sort of pick up the rocks and get all the way back. So it's kind of this idea of there and back again, where you leave a trail behind you when you're going there, so that then you can follow it as you go back. Now there's another part of this story, but we'll just get to that in a minute, perhaps after we follow this first analogy as far as it can go. So in this part of the story so far, Hansel and Gretel leave the little rocks and then they get back. The second part they use breadcrumbs. The first part they use little rocks. So I'm going to introduce you to a new command, which is BL. We're basically doing two new commands today, not a long lecture about commands really, or instructions. The BL command, branch with link. So branch with link is special because it's just like branch. You have BL and a label, but when you execute your branch with link instruction, the address of the next instruction, that is after your BL instruction, is placed into a specific register. So you're saving where you're coming from when you're doing a branch with link. I just might illustrate this with our list of commands. This is the program counter going down. Each of the little lines here is one of your instructions, right? Program counter going down. And you know that this is the BL something. And then you've got your next instruction. So the BL is going to save the value of this next instruction. I guess you could use mobs to save that PC, but you might have to do an offset like PC plus a bit, because the mov would have to be before the branch. So it's really more convenient to use the BL to do this. So this is the first part of the story, really, saving where you were coming from. Now, where is this register that BL is placing information into? You actually don't get to specify this register. We've got a specific one. It's actually R14, but it's usually called LR for the link register. And that's the register that BL always uses to store this location that you need to go back to, the link register. I guess it might start to dawn on you how important this idea of functions is when you realize that one of the 16 registers, its only job is to store data, store the location to return from a function back from. That's its whole job. All these other registers might be used for many things. The program counter is obviously very important. It gets a whole register for that. But this one's very important as well. It's only got one job, and its job is to store the return value, store the location value to go back to once you've finished your function. So when we do this, whoops. Seems like once I go to change slides, I can't get back. We do BL something, then this value goes into the link register. Now the second, I said there were two instructions today. The first one is BL and the second one is BX. Now, actually, just before I go to BX, you've seen BL before because I know many of you have started the assignment and you've seen that there's two functions that you actually branch to in that assignment. One is init, BL space init. So there's a function set up in your assignment template which gets your disco board all ready to play sound. That's the init function. And then there's the other one, which is the BSP audio sample out function, which gets your disco board to send a register value to the digital analog converter and play sound sample by sample. Both of those are functions, you know, because you have to BL to them. And then you also know that once you run them, your code comes all the way back to them. I'll show you a bit more detail about that in a minute, but you've already started using BL. You probably haven't started to use BX unless you've got frustrated in week 3's lab and wanted to start using it. But if the LR register is containing this address that we want to go back to, then the BX instruction is what we use to get back to our starting location in our function. So it's called BX because to stand for the words branch and exchange. A little bit odd, I'll talk about that in a second. But as we were discussing before, to use the B commands, the B instruction, that branches back to a label that you've hard-coded into your program. And the BX instruction branches back to an address that you have stored in a register. So you can BX to any register, but generally we BX to LR. So you see this kind of thing at the end of many bits of code, BX space LR. So we're in history mode now. Don't worry too much about the exchange part. I guess there are a few things in this course so far where when things get a little bit confusing, I start blaming the difference between the thumb ISA and the ARM ISA and the thumb2 ISA. This is one of those times. So BX allows you on some CPUs to not only branch to a different part of code in a register, but also change what encoding your CPU is expecting to execute. So the way that it does that is that it uses the lowest bit. We generally don't need that for an instruction because your instructions can only be 2 bytes long, so we don't need the whole memory address. It uses that lowest bit to indicate which instruction mode we should be in. You absolutely don't have to worry about that aspect of it in this course. We're only using thumb2, and I don't think your CPU disco boards can execute in ARM mode. They can only use thumb2 mode, but it's a kind of relic, just like these stones. So let's put it all together. Let's make a function. So here we've got some code going down, and we're gonna build the +1 function, BL +1. So you're moving, and the number 1 into R0. Then we've got our +1 function defined somewhere else. Where is it? We don't know. It could be anywhere, but our linker knows because we've put a label there, +1. Our +1 function is going to do the work, adding the number 1 to R0, and then it's going to BX all the way back, right back to here. And then we've got some other work going on after that, moving R0 into R4. We know that when you execute BL, the program counter is going to be up to here, right? Or it's going to be indicating the next instruction in your stream. So the program counter doesn't point to the location that you're currently executing. It points to the location that you have to fetch next. So when you do the BL, the program counter is moved into the link register and stored there. And then when you do BX LR, we're taking that LR value and putting it back in the program counter through some transformations. Do you want to do one? Let's just give one a try. I'm sick of reading from slides. Finally, back in Codium. So let's try this. Plus 1, add R0, comma 1, BXLR. That was how it was, right? And I might mov R0, 2, and then I'm going to BL plus 1, and that's all I have to do. Whoops. I sometimes forget and use my Mac key commands on Linux. I should really find some way of making everything the same. Okay, so here we are in my program. I'm going to move 2 into R0. I've now got that. I've got BL plus 1. And when I click step into, it's going to move into that function. And then we're going to add 1 to R0. And then we're going to use BXLR. We know now that there's something stored in our LR. That's our location we want to get back to. And it will take us right back. It takes us right back to the NOP. And we can keep doing this over and over again. Now that we've got a function in our code, we can actually use this other button. This is quite useful when we've got a function, the step over button. Step into means you're going to follow the BL down the rabbit hole, go on the whole adventure with your debugger. But if you press step over, it does the work of the function, but it just hides it from you. So you can just step right over that function call and not have to watch what's going on. You probably have found that out if you're debugging your assignment with all of the BL init. If you step into the BL init, it's going to go down a lot of code. You have to step through it all, very boring. If you step over the BL init, you'll just end up on the very next line of code. Yeah, so one function. We're going to add a few more functions in a little bit, but I thought, let's just get this code started. So what about conditional branches? There's often discussion about conditional branches with BL. You know that when you have the regular branch instruction, you can just add conditions to it and it works in Thumb2, which is fantastic. It's very simple, easy to do. I highly encourage you to use that all the time. In fact, you can hardly avoid it. It's 100% necessary for all of your assignments and exams. If you want to, you can use condition codes with BL and BX, but it's a little bit more complicated. You can't do it straight off. You can't just write BL EQ or BL GT, adding a condition code to it, but you can use it with the IT blocks, if-then blocks that I discussed last week, or sorry, week before last. You can do this if you want, but you can also use regular conditional branches all the time. The IT blocks is something which in previous versions of this course never got spoken about. It was like hushed tones. I thought we may as well just speak about it in this course, and I gave a few slides about it linked there. But you can certainly use those with BL if you want to, and it's going to look a little something like this. BLEQ, block, add 1 to some label. But you have to have the IT, if then EQ, to set up that IT block in order to use it. So it's handy if you want to use it, but it's not necessary. You can certainly get around it just using your regular old conditional branches. So, what happens if you step over a normal branch? Man, very good question. I don't know. Should we find out, Adam? This is just a quick question from Adam before I discuss my function template. What happens if you step over a normal branch? I wonder what we can do here to find out. Add R0, number 3, add R1, R0, R0. I might make a label here and just do some stuff. Oops. I'm doing this little experiment because I've forgotten what happens if you step over a regular branch. I don't think anything happens. It just steps into. Just like doing a regular operation. So the step over is really only useful when you've got a function. I think that's right. One of the tutors can correct me in the chat if I'm wrong. Not always up to date with every tiny detail of the programming environment. So here's the function template. This is something that you will need to remember for your for everything you do in this course from now on. How do you make something that is definitely going to be a function? So the truth of the matter is that functions are very, very simple. They've got two things. They start with a normal label and they end with bxlr. So this is the there and this is the back again. Well, the there is the BL, but you've got a label that you can BL to. And then in the middle, you've got some space where you can do some stuff, do whatever you want. Your program's going to do some work. Now, there's been some questions on the forums. I know that Jasmine has been asking a lot about it. What happens with the type directive? This thing at the top, dot type function name function. So this, anything that starts with a dot when you're in your assembly program is a directive to your assembler. So it's kind of like special commands to the assembler. They're not things that the disco board is going to see. They're just things for the assembler to help it do the right work. The type directive is going to tell the assembler that the following code, the code that follows the function name label, fn name, is what we should call a function. And this is only for the assembler's benefit. It's not for the disco board to see. It's necessary for some things. If you want to disassemble a function and see what's actually inside it, you'll need to have that type directive. Then you also need to have the size at the bottom. But, you know, I just wrote a function in VS Codium that works perfectly. No type directive there. So it's definitely optional. And often I just skip it because, particularly in these little demos, it's certainly not necessary. If you do want to use the disassembly in your debugger when you're writing your programs, if you're writing something that's a little bit more detailed, then you might want to put these type directives in and also the size directive at the bottom of the function to calculate its size. Yeah, so this bit's there just for completeness. It's optional. Big picture here, functions are really simple. Why am I up here speaking about functions for 90 minutes? Because they're important, not because they're complex. They're something in which we really have to get our heads around. I suppose we have to get our heads around the simplicity of them in assembly. I often think that in COMP2300, the difficult part of this course is not that assembly programming is so complicated, it's that assembly programming is so mind-numbingly simple that it takes quite a long time to get your head around the different activities that you have to do. So actually working out what a function is when it looks a lot like your other code, it takes a little bit of mental effort. You have to be able to see in this undifferentiated list of instructions in your program where there's a part where you're branching to something, you're going there and you're coming back again, and it's reusable, a reusable adventure for your code to go on. So if you've got those things, you've got the there and the back again, and it's reusable, then you've got a function. But it doesn't have to be complex. It certainly can be as simple as this 3-line thing that I wrote before. Here's the things. We're using BL with a label to branch with link. That's the there. And we're using BXLR to come back. Only 2 things actually. Oh wow, Josephine has asked an excellent question right now. Can you do a function inside a function? Josephine, I don't want to blow your mind, but I'm literally just about to talk about that, so this is going to be fun. Yeah, This is where we get to the analogy, a second analogy. I suppose a few of you play games. I know there's some people on Twitch who definitely play games because they've got their Twitch accounts all set up. But just for context, I think my favorite game of all time at the moment is Breath of the Wild. But another favorite game of mine is Skyrim. Here's a Skyrim image, just for some context. Everything's going fine there, right? Yeah. Oh, come on, just want a full screen image of Skyrim. Yeah, so in Skyrim, you're this person, the face is turned away. This could be a man or woman or a lizard person or a snake person or an orc or anything. You get to choose who you want to be in Skyrim. Oblivion was better, says someone. I don't know. How do I play Oblivion? I only have a Switch. Full disclosure, I have purchased Skyrim twice, once on PS3 and once on PS4. I have been close to buying Skyrim multiple times on Switch. So the reason I keep doing this is because I really enjoy exploring this world of Skyrim. But I'll tell you what keeps happening with Skyrim, which is a bit embarrassing, is that there's all of these different kinds of adventures to go on, and I have never actually completed the game, as in completing the main story. I just get distracted by many adventures. So it's all of this going there and coming back again, which gets me distracted. And in fact, something which really frequently happens in Skyrim is that I will be given a quest by some other character in the game. Okay, go find this ancient burial temple by the ancient Nords, and go get in there and get some kind of treasure or meet a ghost or defeat a troll or something. And so I go to this place all the way there, and then as I'm going there, I meet some other character who says, well, actually, I'd like you to go to my mine and defeat all the spiders. And then I'm going to the mine and defeating all the spiders, and on my way there, I end up on some other quest, and then, right, so then I've gone on a lot of theirs, and I never get all the way back again. And in fact, sometimes I put the game down for a while, days or weeks or months or years, and then come back to it, and I've forgotten what all my theirs were, and so I can hardly get back again. So this keeps happening to me in Skyrim. I'm sure it's not an uncommon occurrence, basically with these games where everything is like a little fetch quest, endless quests on quests. It's very easy to get lost in all of the return parts. And so this is something which is about to happen to us in functions, actually. Because what if we wanted to have a function within a function? So we go inside our function to some other place in memory, and then during that function, we want to use another function and go somewhere else in memory, and then return back here. So this is like getting a sub-quest during our first quest, and then we've got another sub-quest and go there, and then we finally get back again to our original place. So yeah, when you forget to add the base case in your recursive call. We're not quite getting to recursion yet, melodic maple, but we will get there on later this week. But so far we're just doing nested functions. I guess the functions within functions are so hot right now, but they're a little bit tricky in assembly. We do have to do a little bit of extra work to get this to happen. So let's go through carefully and see what's going to happen. Recall with Hansel and Gretel, the first time they went on their adventure, they were taken into the woods by their parents. They found little pebbles to get back. Of course, they get home and the parents are like, well, what are you doing here? We were trying to get rid of you. And they take them right back into the woods again. But this time, Gretel didn't have time to pick up little pebbles. But she had a great idea. She thought, I'm going to use breadcrumbs. I'll crumble up some bread and we're going to be able to get ourselves home that way. Of course, as you know, if you just scatter some bread around a forest, it doesn't last long. Birds came and ate it, and they couldn't get home following the breadcrumbs. And they ended up having another adventure involving a witch involving avoiding being eaten by a witch, and then involving defeating the witch and living happily ever after. So that's good for Hansel and Gretel. This same thing of birds eating our breadcrumbs, or something like it, is just about to happen in our functions. So let's go, I just want to do this in code. It's more interesting that way. I'm going to delete the stuff here. We've got our +1, and then I want to make another function, which might be, mult2. So I have two functions. Mov r1, 2, mul r0, r0, r1, bxlr. So I've got two functions now, +1 and mult2. Now if we do these functions one by one, if we're very good Skyrim players and we only do one quest at a time and we complete each quest before we start another one, then things should be fine. Okay, we're going to put 2 in R0. We're going to add 1 to it. We've got 3 in R0. Now we're going to mult2. Go to the second function. We've got 2 in R1. Do the multiplication. And then go back. So now we've got 6 in R0. So far, so good. This is fine. What if we did things the Charles way and just did whatever quest takes our fancy? So we... Oops. We start off with +1, and then after we do our +1 inside the second function, we want to mult2. So we're BLing +1. Now the link register has this NOP as its address that it's storing. And then we're going to do the add 1. Now we're going to go to mult2. Now the LR address has this line of code as it's storing. We can't store two things in LR. Now we're going to do the multiplication, and then we BXLR, and now we're back here, but what happened to the first LR? And I don't know where we are. It stopped working. So we BXLR to somewhere that we don't know. So we weren't able to do this kind of functions within functions so far. So this is just what's happening now. You can certainly, if we go inside here, our LR is getting overwritten by these interior BLs. So we have to do something about that. This is a broken version. Yeah, I BXLR'd way too much on The Witcher 2, Frosty Winter. I'm deep on too many BXLRings, and I don't know where I am in The Witcher anymore. So maybe you guys could have a chat about it. Talk to me in the chat, Teams chat preferably, just so we can all stick together. How can we stop the first return address getting clobbered? So this is chat time. Chat question. How do we stop the first return address getting clobbered? And when I say clobbered, I mean it's getting overwritten by a subsequent return address. Because when we're over here, this BL is moving this thing to LR. We've only got one LR, right? Then when we do this BL, that's going to put this one in LR. And then it's clobbered. Yeah, very good idea, Gabe. We could just store LR in R10. Very, very clever. Yeah, Robert MacArthur says a stack would be useful. Good idea. Store the address somewhere else and then reload it later. That's right. So we're going to have to store our addresses somewhere useful and get it back later. Spoiler alert, stack exists, says Adam. Gabe says push and pop. Yep, we're getting to pop and push on Friday, but let's just go through this step by step. I guess what we're trying to do with this lecture is slowly build up these concepts so that I'm not just like, oh, there's a stack which exists and these are the things you do with it. I want everyone in the class to understand not just that it exists, but why it exists and why we need it, why we can't do without it. It's every one of these components is not just there and useful, but actually necessary to do computing in the way which we want to. Yeah, excellent ideas. So I guess Gabe has got a good one there, talking about putting our link register somewhere in particular. We're going to put it in R10. So we could store it to memory, right? These are the various variations on that theme I'm seeing in the chat. One idea was to put it in a different register. One idea was to put it somewhere else in memory. And somewhere was to put it in something called the stack, which we don't know about yet. So we'll just consider that to be a different kind of memory. So here's a good idea. What if we store it in some place in memory? So when we start our +2, we're going to put the LR value into memory, and we're going to put it in a place defined by this value SP. And then later on, we're going to load it by this value SP. So if you don't know, then this SP is a location in memory for a specific part of memory called the stack, which we're going to talk about at length in this course. It's really, really important. But in this code so far, we're just treating it as a regular memory address. That's OX something, right? A regular memory address, and we're just going to put some our link register there, and then we're going to load it back. So this is I think Mitch has just brought up this point about storing it in R10 or storing it in this location itself. This is going to get us out of trouble in some sense. We can store it somewhere special. We can store it in the stack and load it back. We can store it in R10. But if we go deeper and deeper and deeper, we might get into trouble with that as well. Whoop. Let's just give this a try. If we store this in, well, let's do this the way I've suggested in the slide there. Store LR SP for stack pointer, and then after this we can letter LR SP for stack pointer. So if I run my code now, you can see the stack pointer is pointing to something. That's a memory address, which is where our stack starts, 0x20018000. Going to mov 2 into R0. We're going into our first function. First thing we do is take our LR and put it somewhere safe. We're going to put it at the top of the stack. And then we're going to add 1 to our value. Oh, I've done something wrong here. What did I do? Someone will tell me in a minute. Yeah, Adam, you're absolutely right with that. This is not going to work if we nest more than one level. Why is that not working? I'll get back to that later. We might do a stream on these things once I get it to work properly. Well, back on the stack idea, the problem here, as Adam has pointed out, is that if we're just using one particular location in memory to store our LR, or in fact we're using a register, we can certainly put it there and get it back, but if then our sub function, which we call, also wants to use that location, then we're stuck because we're going to clobber it anyway. So the point of this is to use something called the stack, which is a bit of memory which we're going to use to get things done. And the point of the stack is that you can put something there and then put another thing there just below it and sort of remember where you're up to in this stack so that you don't ever overwrite something. So you've got a stack pointer which is kind of remembering where you're up to in the stack, and as you're adding data it's sort of moving down through memory, and then as you're using your data or grabbing it back, your stack pointer goes back to where it was. So you're not going to overwrite things that you've already stored there. This is a little bit of a sneak peek of the stack because we talk about it more in the second half of this lecture, or the second half of this topic. But SP is another one of these registers which has a special name and one special job. So it's actually R13, but SP gives it its only job, which is to remember where you're up to in the stack, so you never get lost. So your stack is going through memory, you've got some data that you've stored there, and you can also always add something to the stack and the stack pointer moves to where you're up to. There are some people in the comments saying, oh, we've got this push operation and the pop operation, and these are great operations for kind of helping you out with your putting data on the stack and taking it back. When you push to the stack, it writes what you want to put there, moves the stack pointer, and when you pop from the stack, it reads what you had just written and moves your stack pointer back. So by convention, this SP is an address in the SRAM region of your address space, just like .data. You can certainly write all over it if you want to with other commands. It's up to you as an assembly programmer to not do that if you like using the stack in this kind of civilized way. But basically, the stack is going to be the main bit of memory you use to get things done within a function and to kind of behave in a civilized manner so that you're not accidentally writing over other people's memory. And it's really important in doing functions. It's going to be particularly important when we do recursive functions, because you really can't do recursive functions without using the stack properly. So we're getting back to the stack later. This is all I need to say about it at the moment, but we can certainly use this to get ourselves out of this problem with the link register. So maybe some of you might have felt a little bit lost about the stack thing in particular. There's been a lot of new terms about the Disco board today. I guess today we've only covered 2 instructions, but we've covered a lot of different ideas of different places to store things in memory. But you're going to write a lot of functions in this course. Assignment 1, you don't particularly have to write functions, although it could help. But in assignments 2 and 3, you definitely have to write them. You've got a whole lab dedicated to writing functions, and you'll have to write a lot of functions for the other assessments. So it's something that you're definitely going to get used to in this course. Now at this point, maybe we could have a little break and a general time for questions. So feel free to jump into the Teams chat and ask me a question if anyone feels like it. I've got another little topic for today, but I just want to take 5 minutes to rest my voice. I have a question. Why isn't my code working? Ah, man, yeah, Mitch is exactly right. I should have remembered. SP starts with a memory address you can't actually use. Push subtracts 4 first. Oh. So I can't use SP. That's one of these classic things in these slides where something is written out in a way that makes sense to explain it as a concept, but when you actually try to implement it, it's not quite right. So let's just use a different memory address. I'm going to say mov R10 OX, just the start of SRAM. How about that? Okay, here's my demo. I'm just going to define the start of XRAM in R10 so I can use it. And then I'm going to put 2 into R0, plus 1 into there. I'm in my function. I'm going to store my link register in that location in memory, which is currently stored in R10. Then I can add 1 to R0. Oh, I got an infinite loop again. Why didn't that work? Still stuck. Someone else can help me fix it. I'll just skip to the stack way of doing it. None of zeros is in R10. Wasn't there? One, two, three, four, five, six, seven. It's all these little mistakes. I should just keep putting questions on Piazza. I'll try it one more time. If it doesn't work, I'll quit. Okay, that looks better. Now it works. I should have Mitch next to me all the time to debug my code. Thanks, man. Now I can do my mult 2. So I've got 6 there in R0. And then do BXLR, takes me back. Now I'm going to get back the LR that I'd stored before in R10 from memory, OX20000. And that should work. BXLR. Finally, we got it to work. So one function within one function. So we did get this to work finally. Now we can try. Yeah, so I guess the reason that you don't want to rely on this method for getting around this problem is supposing you had some other function, you'd said that R10, this location in memory was the location I was always going to store my link register, my second link register. But then you had another function which also stored it in R10 and then got back that way. Oops. Now we're just doing the same thing. So it's very easy to make this mistake where we think we can get out of a problem, but when you're actually doing some significant programming in assembly, you might have quite a few functions which call each other. Particularly if your code is nice and modular, we all like modular code divided into functions. So yeah, we're going to have to work out some way of kind of automatically moving down a data structure to keep adding LRs where we need them and getting back later. Okay, cool. Maybe I'll go on to the next topic then, if everyone's cool. Yeah, boy, thank you so much to everyone who's participating in the live stream right now. It's really fun to feel like we can still have a live lecture even though we can't meet in person. So for the next little topic, we're going to talk about calling conventions. This is going to address I guess, the next two open questions in my little list of questions about functions. So first of all, we've worked out how does the program need to know where to come back to. That was the LR bit. Now we want to work on how do we pass information into our function and how do we get information back. And I guess another implicit question is how do we write functions so that we avoid messing up every other part of our program? Because as you know, when you're writing an assembly, you have to write instructions that use registers. And if you're writing a function, it's going to use registers as well. So if you've got your program up here using all your registers, how can you make sure that your function is not going to just overwrite the registers that you were already using? And that's something which I think some of you have started to twig to when you were working on assignment 1, is that when you branch and link into a function, sometimes there are registers that get changed and you can't expect your values to be there when the function returns. And that normally doesn't happen when you're programming, or we'd like to avoid that happening. That you like to avoid side effects, as Oscar has just said in the chat. And I guess in assembly we can't avoid side effects all the time because there's a limited number of registers, there's a limited amount of memory, and we have access to all of it. But we can perhaps follow some standard guidelines or conventions that mean that we are not going to mess up other parts of our program when we're using functions or using reusable bits of code. So let's assume x is in R0. Now, this is something we've put in a lot of the slides so far in this course. I've often written something like, here's a few lines of assembly which are going to add 1 to x, and you can assume that x is the number which is in R0. So this makes sense between you and me, right? As we're humans, we can read the context, we read the comments to understand what a piece of code is supposed to be doing. But does this make sense to the assembler? Does it make sense to the disco board? Well, no, because the disco board can't read the comments, and it can only understand the assembly instructions that are translated into CPU operations. So the question is, how do we work out some guidelines so that we can always know what should be, where x should be if x is coming into a function? And this is what our calling convention is about. So what we need in order to make these assumptions about how functions should work is a convention, or kind of rules of doing business, rules of engagement, an agreed upon plan for where to find inputs and where to leave the outputs when our function is finished, so that all of our bits of code can play nicely together, right? Now, I've got a very outdated slide right now because this is 100% banned. You're not allowed to do that. No handshakes, not even elbow bumps. Elbow bumps were like fashionable for about 10 days and then everyone realized, just don't. This person is obviously way too close. That needs to be greater than 2 meters. I think that we can't, there's 3 people in this meeting room right now. 1, 2, 3. They're at work, which is also a no-no. So, we obviously have to, well, I guess this is something which has been happening recently because we all are working from home, we're going into different places, but we still want to do our study and our work. We've had to work out new ways to engage with each other, new kinds of conventions. But the calling conventions for assembly have so far been unaffected by this international health emergency, but we can definitely rely upon them to be the same, although our regular business conventions cannot be. So the rules of doing business in your functions and the rules for writing up code in your assembly is something called a calling convention, or a CC, often used We often use CC to abbreviate that. We'll see in a minute we get our particular CC for ARM. And this is going to be some kind of contract, I guess. It's not legal. It's just a list of rules that if you follow, then you can sort of have some assurance that other bits of your code is going to play nice. And the contract here, or the agreement, is in some meta sense between us as programmers, but you're really making an agreement with yourself because you might be the one writing the functions and writing the bits of code that call the functions. And here we get to two little slightly annoying words, which is the caller. That's the code which makes the function call. That's the code that's doing the BL. And the callee, which is a bit of code between the label and the BXLR instructions. So the callee here is the function, and the caller is the code which is calling the function. Of course, you may think, well, these are all in the same file. They're all the same bit of code, but we're just going to have to sort of give these bits of code in our file different personalities for a minute. So back to my examples. Mult2 is a callee. +1 is a callee. Main is a caller of +1. +1 is a caller of mult2. And main is also a callee because it's a callee of startup underscore stm32L476xx.s. We can find it in here. Main. See? It's getting called. BL main. So main's a callee and a caller. So the same bit of code can be both, but they're a callee with respect to a different part of the program. Yeah, they're going to be... Someone's just asked in the chat whether we refer to callees and callers within recursive statements. I think we do. That's just going to get very confusing. There's a lot of things where when you go on a long recursion, the normal words we use to refer to things break down a little bit, but this is the way that the convention works. When you see callee and caller in these documents, you just have to understand that what the callee is, that's the function, the code inside a function, and the caller is the code which is calling the function. So what does the calling convention specify? Where to look for the parameter values, the inputs to your function, where to leave the outputs when you're done doing your function work, which registers that you're allowed to mess with and which registers you shouldn't mess with, or you have to, if you're going to use them, you'll have to store their values and put them back later. And yeah, so I guess we got a little talk box here. Maybe I won't go through this one, but the idea here is to just have a think about which calling conventions this function's using. So it's a function written in kind of C-ish or Java-ish language. And it's called do all the things. And then you've got an int with an input that says how many things, and then actually it's doing none of the things in this comment, and then returning 0. So is this function using our calling convention? Does this make sense? Oscar says in the comments it's a bad CC. I think we're just adding e's and ers for each case. So maybe maybe this was a bit of a trick question, right? Because in some sense, this function is it's doing a calling convention correctly because it is definitely returning an int, which is what it said, and its input is an int. But what it's advertising it's going to do here, it's not actually doing. But our calling conventions tend not to actually be to do with what the function does. It's just with where it's putting certain data. So they work at a bit of a lower level than the obvious lies in this function. So although this function is misusing one convention, which is if you have your function name called something +1, you would certainly expect that it actually adds 1 to something. This one says it's going to do all the things, it's actually doing none of the things. But that's not what our calling convention is about. Our calling convention is about where the parameter values should be, where its output should be, and which registers we can use. So this function doesn't do anything wrong in those respects as far as we can tell. It's doing something wrong at a higher level. So the big picture here is that there are lots of conventions in programming. Some of them are ones that are between different programmers. If you write an API, we certainly expect that that API should work. If you deliver some code, we certainly expect that it should compile and run correctly. But our convention that we're talking about here is for the very lowest level of interaction between different parts of your program. And in some sense, it doesn't matter which calling convention we're using, as long as the caller and the callee are using the same convention. So we have a particular one for ARM, which is already set up for us. That's the one we use in this course. But you can invent your own one and use that if you want to. There's no problem, except if I'm looking at your code later and trying to understand what you're doing, that's definitely going to confuse me. A few little examples of calling conventions here. So we've got two calling conventions with 2 + 1 functions. Are both these functions going to give the right answer? They're both +1, so they should both be giving x + 1. What's the difference here? Well, this first +1 function is going to add 1 to R0. So we can assume that R0 is the input here, and we can also assume that R0 is the output. So in the second one, we can see that R2 is going to be the input, and R5 is going to be the output, because that's where the addition is going to go. So the difference here is which registers we're using for the input and which ones we're using for the output. I guess a question for you is, which one of these would you find more confusing? And I would definitely find this one more confusing, because like R5 and R2, they just seem quite odd numbers to choose. Maybe this would make sense if your program so far had been using R5 and R2 for specific things, but R0 and R0 maybe make a little bit more sense in terms of where to be leaving data and where to be taking it in. R0 is like maybe our most used register, right? We're using it for all the things we can think of. So now we get to, this is where I actually explain the calling convention. The ARM v7 architecture procedure call standard, AAPCS, is the convention we generally try to adhere to in programming our disco boards. You can read the document, it's linked here, it's in the website. It's quite long. It's got a lot of information about different things you might need to do when you're writing assembly code in ARM v7 architecture. But the general summary is this. The most important bit is what can you do with certain registers? So under this summary, R0 and R3 are the parameter and scratch registers. So you might use the R0 to R3, R0, R1, R2, R3, 4 registers. They're the parameter and scratch registers. That's where you're putting information into your function. You use that with the BL to the sample out function in your assignment. R0 and R1 are also the result registers. So you've got 2 result registers to get information back. R4 through R11 are the callee save registers. So that means that the function itself, the callee, they can use those registers, but if they want to, they ought to be storing all the information in those registers and then putting it all back when they're done. So as if nothing had happened, right? You go into a room, you mess everything up, you come back and put it all back the same way. And then R12 through R15 are the special registers, IP, SP, LR, and PC. We know what PC is, program counter. We know LR is link register from today. We've learned today that SP is the stack pointer. And then IP is another one. It's the interprocess link register, I think. Interprocess something. Charles minus 1030, I know, we're done. We're very much done. This is the last slide. The IP is another one. You tend not to need to use that one, but it is also a special register and used for special purposes. Mainly if you're writing a compiler, you would care what IP is. So this is the general summary. Now, the last thing I'll say before we finish is that these four registers, parameter and scratch registers, a function is allowed to mess up with those registers, and the person calling the function, the caller, can't expect things in those registers to be the way they are when the function returns. So if you've used R0 to send a value to a function, and then you call that function, and then the function returns, you can't expect that R0 is going to be the same. The function may have used it, and the procedure call standard says that the function doesn't have to fix it up. So it's your responsibility to make sure that if you've got important information in those four low registers, that when you call a function, you save it somewhere else. So we'll talk a little bit more about this later in the week. This is all I wanted to do today, and we will get back to a few more details later. I guess I'm just going to go back to the question slide, and then we can have some more chat times. I'm going to call that over.